This lecture is on linear functions in space. Now, you recall in single variable calculus, you had y is equal to mx plus b, and in a similar notation, you had y minus y naught equals m times x minus x naught, and if you solve for m, you get y minus y naught, which is delta y, over x minus x naught, which is delta x. So in multivariable calculus, we're going to be developing similar equations. Now, in single variable, linear functions are lines in the plane. In multivariable calculus, you have two types of linear functions. The first is a line in space, excuse me, and the second type is a plane in space. All right, so let's start with a line in space. Okay, and I'm going to develop these equations using vector notation, and then we'll translate that vector notation into scalar notation, something that you're more familiar with. So, let's start with R3, X, Y, Z, and let's say here's our line in space, and it goes on forever in both directions. So to describe it, we need a point, and let's say the coordinates of this point are x naught, y naught, z naught. Okay, that gives us a starting point, and now we need a direction. And we're going to specify that direction using a vector. We'll call it v, or vector. And it's going to have coordinates, say, A, B, C. So it's A over, or A towards the front, B over, C up. And we use the square brackets for vector notation. Now we're putting this vector starting at the origin, so we call that a position vector. But this vector could be anywhere as long as it's pointing in the right direction. So we could even think of it as being here. So this is vector V. And that's the point. So you can think of this line as just points, starting with this one. And then, well, one more thing we need. We have this vector here, and let's call this vector R naught, and it's going to have coordinates, well, it's going to have coordinates x naught, y naught, z naught. Okay. So you can think of this line in space as this point, and now if you took this vector and added this vector, you would get this point, right? And then if you said, I'm going to go with this vector, but only half this vector, you would have this point. Or two of these, you'd have this point over here. Or minus one of these, you'd have this point over here, etc. So how do we write that? Well, for a line, let's say the notation is going to be R. Okay. Now R, remember, is just by definition the arbitrary x, y, z vector. So what's it going to be equal to? Well, we're going to start with R naught, and we're going to add to it this vector. So we have R naught plus this vector, so that's vector V. But we want one of these, a half of these, two of these, minus one of these. or simply we're going to multiply it by some scalar t, called a parameter, and we're going to let t vary from minus infinity to infinity. So this is the vector equation for a line in space. Now, we can kind of expand this notation because R is just x, y, z equals R naught is just x naught, y naught, z naught. And then we have plus the scalar t times the vector v, which is just a, b, c. All right. So we can write the right-hand side here as a vector. When we add vectors, we have x naught plus a times t. And then the second component is, of course, y naught plus b times t. And finally, z naught plus c times t, end bracket. So what does that mean? Now we're just going to transcribe this from vector notation to scalar notation. So this component equals that component. So I'm going to write it up here. So x is equal to x naught plus at. Y is equal to y naught plus bt. And z is equal to z naught plus ct. Okay? So this is the scalar representation of this line. You just let t vary from minus infinity to infinity. And these are just numbers. A, B, C, x naught, y naught, z naught. Okay? So here's the scalar representation, here's the vector representation, and here it is expanded. Okay, so that's a line in space. Finally, we'll do a plane in space. Okay, so it's the same stuff here, x, y, z. And let's say the plane looks something like that, and it extends in each direction forever, let's say. So what do we need to describe a plane? Well, we need a point. Again, that's going to be point x naught, y naught, z naught. We call it a particular point. And this time, a vector in a plane isn't going to do it. What we need is a normal vector. So a vector that's perpendicular to the plane. So we'll call that n, big N, vector. And let's say it has components A, B, and C. Okay, A, B, C. Now, what's going to make this work is, well, first we have to identify an arbitrary point. This is a particular point in the plane. This is an arbitrary or general point. So let's let this guy have coordinates x, y, and z. So these are variables. These vary. So, what's this vector? Well, we'll call that, well, let's just write it out. This vector, with respect to x, it goes from x naught to x. So that x distance it travels is going to be simply x minus x naught, that value. And similarly, we have y minus y naught, and z minus z naught, end bracket. All right. Those are the parts that we need. So I'm going to need a little space here. This works when, well, by definition, this vector and this vector are perpendicular. Okay, so there's a right angle here. Now, two vectors are perpendicular if and only if their dot product is 0. So we'll take this vector y minus y naught, comma, z minus z naught, and we're going to dot it, and I'll finish it here, with this vector ABC. And by definition, that's got to be equal to 0. So this dot this is 0 because they're at right angles. So, in case you haven't seen it, to do vector dot products is very easy to do them algebraically. We just take the first component, multiply it by the first component, plus the second times the second, plus the third times the third equals 0. So very quickly we have A times x minus x naught plus b times y minus y naught plus c times z minus z naught, and that's all equal to 0. So now let's multiply this out algebraically. So we have ax, and I'm going to skip this, plus by plus cz. Okay, now we have minus ax naught minus b y naught minus c z naught equals 0. Okay, now a, b, and c are just numbers, and x naught, y naught, and z naught are just numbers. So this is just a number. So we'll call it not d, we'll call it minus d. So when we put it on the other side, it becomes d. So finally, we have, I hope you can see it, I'll write it up here, ax plus by plus cz is equal to some number d. And this is the linear equation for a plane. Okay? And the coefficients a, b, and c are the coefficients of the normal vector for that plane. So that's all there is to it. Thank you. End of lecture.